Hello students, welcome back. In this video, we are going to discuss circular queues. We have been discussing queues for quite some time now, and we discussed in the last video the drawbacks of linear queue. So the drawback of linear queue is though the queue is full, though there is space in the queue, we conclude that the queue is full. There is no space in the queue, right? So for example, if you see this queue, this is our queue. This is our data array 0, 1, 2, 3, 4, and this is F, R, and let's say we do some NQ operations 10, 20, 30, 40. So F is 0, R is 3, let's say. Right? Now, if I perform some DQ, but let's say I perform DQ twice. So when I perform DQ, I delete this, F becomes 1. I delete this, F becomes 2. Right. Now let's say I perform two NQ operation, right? NQ, let's say 50, 60. So R will increment, R becomes 4, 50, right? Now, in order to NQ 60, I want to NQ 60. What is the procedure? Procedure is see what is R, right? R, and R is equal to 4, and last location is also equal to 4, right? So when R is equal to last location, right? When R is pointing, in fact, it's not pointer, but R is storing the index, last index, array's last index, that is 4. So we conclude that this queue is full. So R is equal to size minus 1. Size minus 1. Size is the size of this array. So R is equal to 4 in this case, right? So we conclude that the queue is full. When this condition, what is the condition? Queue full condition here? Queue full condition is rear is equal to last location or last location index, right? R is equal to last location index, that is the queue full condition, right? Now R is equal to 4, last location is also 4. So we conclude that the queue is full, right? Now, but if you see, actually, there is space, right? There are two empty spaces here. There is no element here. We have removed this. 10 is not there, 20 is not there. So these locations are empty. But still, we are concluding that the queue is full just by looking at R when R is last location. So this is the drawback of linear queue. Drawback of linear queue. Right? What is the drawback? Though there is space in the queue, we conclude that the queue is full. Right? Now, why it is happening? It is happening because we are saying that when R is last location, the queue is full, right? Though there is space. Now, in order to overcome this drawback, right, whenever our R reaches to last location, we will wrap this R around and we'll bring this R to the beginning, right? Whenever R goes to last location, right, and if we want to perform NQ operation, what will we do? We will wrap this R around. That means we will make this R 0, right? We'll make this R 0, that is the first location, and then check, is this location empty? If this location is empty, then we'll insert here or we'll perform NQ here. But if this location is also full, then we'll say that the queue is actually full, right? In this case, R is 4. I wrap this, rather than concluding the queue is full, what I do, I wrap this R around. That means I give this kind of movement to R, right? In the previous case, in the linear case, R was incrementing only in this direction, right? Whenever R was, let's say I, after incrementing it was becoming I plus 1, right? In this direction only it was going. That's why it was called linear queue. But here, whenever R reaches to the last location, we will give this moment to R, and this moment is called as circular moment. Circular moment, right? So when R becomes 4, we'll make it 0. We'll make it 0, and then we'll see, is that 0 location actually full? Is an element present there? If an element is present there, we'll say that the queue is actually full. And if the element is not present there, we'll say that the queue is not full. So this kind of movement we will call as circular movement, right? And because of this movement, this queue will be called as circular queue. Actually, the queue is same. Everything is same. The same data structure we are going to use. Same data structure, right? So the same array 0, 1, 2, 3, 4. This is data array. This is queue. Same F, same R, right? Everything is same, right? Only thing is whenever our R reaches to this location, in fact R and F both, right? Whenever they reach to the last location, we will wrap them around like this, right? We'll bring them to the beginning. And because of that movement to F and R, we'll call this queue as circular queue. There is no change in the implementation at all. Everything is same only because we are giving this movement. That's why this is called as circular queue. Now the question arises, how can I give this circular movement? How can I give this circular movement, right? In the linear queue, we were saying that R is equal to R plus 1. F is equal to F plus 1, right? So F and R were incrementing linearly, right? But in case of circular queue, F and R will increment linearly up to last location, right? Up to last location, same linear movement. Up to 4, same linear movement for F and R, right? But as soon as this F and R reaches to last location, and when we want to increment F and R, we will give this circular movement, and that can be given by using this formula. R equal to R plus 1 mod size of this array. And for F also, F is equal to F plus 1 mod size. Right? So this, by using this formula, I can give this kind of movement, right? To F and R. See, R plus 1 same like this, right? F plus 1 is also same like linear queue, but this formula will come into play only when F is last location and R is last location. And this formula will behave exactly like this formula till the last location, right? Till we reach the last location. Let us see. Now let's see, our F is 0, R is 0. Let's say we have an element here. Now this, let's say we want to enqueue 20, 30, 40 and 50. We want to enqueue this. So now let's do the comparison of this linear. This is linear and this is circular movement, circular queue, right? So see, the name is only because of this kind of movement. There is no change in the data structure at all. Only the movement of F and R is differentiating, right? So this is linear movement, this is circular movement. Now let's insert 20 by using this linear. If I want to insert this 20 by using linear, I'll say R is equal to, R was 0, R will be 1, R plus 1, right? R plus 1. So now in case of circular, if I do the same insertion using circular movement or circular formula, what will be R? R equal to, R was 0, 0 plus 1 mod, what is size? Size is the size of this queue or this array, 5, right? So 5. So this is 1 mod 5. What that this mod will give us remainder. This mod will give us remainder. When I divide this 1 by 5, the remainder is 1, right? Now R is equal to 1 in this case, and this case also R is equal to 1, right? By using both formulae, like this and this, the same result I'm getting, right? Now we'll insert 20 there. Now to insert 30, if I use linear, R is equal to R plus 1, which is 1 plus 1, 2, right? If I use circular, R is equal to R plus 1 mod size, that formula I'm using, right? Let me use one other color. So R is 1, right? R is 1. So 1 plus 1 mod 5, 2 mod 5 is equal to 2, right? When I divide 2 by 5, the remainder is 2, quotient is 0, right? So this is the remainder. Mod will give us remainder, right? So here also I got 2, here also I got 2, right? So I'll insert this 30 at location 2, right? Now let us insert 40. In order to insert 40, we'll increment R by using linear increment. So R will become 3. And if I increment by using circular, I'll get the same thing, right? R is equal to 3 here also, right? So 3 and this 40 will be inserted here. In order to insert 50, R will become 4, right? By using linear, and by using circular, R will become 4, right? And we'll insert 50 there, because when I use this formula, R was 3, 3 plus 1 is 4, 4 mod 5 is 4, 4 mod 5 is 4, right? I'll get 4 here also. Now let us say I want to insert, let's say 60. I want to insert 60, right? Now if I use linear, right, what is R? R is equal to R plus 1, right, which is equal to, R is 4 already, right? R is 4. 4 plus 1 is 5. So I'll get 5, which is not in this array. Fifth location is not in this array, so we are going out of the array, right, because of this linear increment. But if I give circular increment to this, right, circular increment is R is equal to R plus 1 mod 5, which is size, right? R is 4, so 4 plus 1 mod 5, that is 5 mod 5. When I divide 5 by 5, I get quotient as 1, and this will give us a remainder which is 0. So R becomes 0 in this case, right? Here R was becoming 5, here R is becoming 0, right? For inserting this 60, right? When R was already 4, if I give linear increment by using R equal to R plus 1, I get R is equal to 5. But if I use this formula, right, R becomes 0. R becomes 0. That means I am going here, right, like this. R is this location, right? So you see, up to this, in fact this, the moment linear and circular were same, but when R is equal to last location, linear will increment R and it will become 5, but this circular formula will make R 0, right? Now that is helpful. When I get R equal to 0, I will go to 0th location, and why I'm doing that, I want to go back and see, go to the beginning and see, are these location occupied? Now in this case, F is also 0, right? F is 0 means there is an element present here. There is an element present here, F is 0, right? So when I increment R, R becomes 0, and that incremented value of R is equal to F, right? Incremented value of R is 0, circular incremented value of R is 0, and if that is equal to F, then I will conclude that in this case the queue is actually full. The queue is actually full, right? Now this is queue full condition here. What is queue full condition here? If I increment R by using circular formula, and that incremented value of R is equal to F, right? What is the incremented value of R here? The incremented value of R is 0. And if that 0 is equal to F, F is also 0, that means there is an element. When F is 0, that means there is an element present on F 0 location, right? And I'm checking 0 location, right? So incremental value of R is equal to F. The queue is full. This is the queue full condition. Then when the queue is not full, let's say now I perform before incrementing this. Let me take another situation here. Again, let's say I'll take this queue. This is data array, F and R. Let's say I perform some NQ operations in this queue by using circular formula, right? And 50. Now in this case, F will be 0, R will be 4, right? The formula which I am using is circular queue formula. R is equal to R plus 1 mod size, which is 5 in this case. And for F also, I am using this circular formula. F is equal to F plus 1 mod size, right? Now let us say I perform some DQ operations. Let's say I perform some DQ operation. So what will I do? What I do while performing DQ operation? I'll remove an element from 0 location, F location, right? So I'll remove this, right? I'll remove an element from F location. F is 0, so 0 location I'll remove an element, and then I'll increment F. In case of linear queue, I was incremented F like this using this formula. In case of circular queue, I'll increment F by using this formula. So what is F now? After incrementing, F was 0 already. 0 plus 1 mod 5, that is 1 mod 5, which is 1, right? When I divide 1 by 5, the remainder which I get is 1. So f becomes 1. In fact, this is same as linear increment. So this will same as linear increment till this location, right? Okay. Now, I mean, by till last location, when we increment at the last location, it will wrap around, right? So, so this is f. So I have incremented this, right? Now let's do one more dequeue operation. Again, f is 1, remove from location 1, and then increment f. Then increment f. So dequeue operation, I hope you remember. Dequeue. First remove from f location in data array, right? And then increment f, right? Then increment, after removing, increment f. Of course, if I'm making sure that the queue is not empty, then only I'm doing this, right? And in case of enqueue, first insert on R location. Sorry, first increment R, not it's not like that. First increment R, right? First increment R, then insert. Okay? That means whenever you want to enqueue, you make R equal to R plus 1 and then go to data array and data of R you do. But in case of dequeue, first get element from data array from F location and then increment F equal to F plus 1. In case of linear queue, here first get an element, then increment, here first increment, then insert an element, right? Okay. I'm sorry. So now let's perform one more dequeue operation. I'll remove this, I'll erase this. I just wanted to show you, remind you the process of enqueue and dequeue operations. Okay. So if I perform one more dequeue operation, dequeue, what happens? I'll get an element from F location. F is 1, so I'll get this 20. Right, I'll remove this 20 and then increment F. So F will be incremented in circular fashion. F is 1, 1 plus 1 mod 5. So 2 mod 5 will be 2, right? So F becomes 2, right? So now F is 2 means these two locations are empty. R is 4, right? So this is the queue. Now let us see, we want to enqueue now. Enqueue 60, right? Enqueue 60. Now, had this been linear queue, what will we do? We'll say R is equal to, we'll first check if the queue full, right? We'll first check if the queue is full. R is equal to 4, and is this equal to the last location of the array, right? Last location of the array is 4. That means R is equal to 4, which is equal to last location, right? R equal to 4, which is equal to last location. We will conclude that the queue is full by just looking at the value of R, right? And comparing it with the last location of the R. Last location is size minus 1, right? If R equal to size minus 1, we say that the queue is full. Queue full condition in case of linear queue is R equal to size minus 1, right? So size minus 1 is 4 and R is also 4, the queue is full. But now in case of circular queue, what we do, right? We increment R, the queue full condition here is, right? Queue full condition, how will I check whether the queue is full or not, right? I'm telling that R is equal to by first increment R, I say R equal to R plus 1 mod size, this formula I'm going to use, right? And then I say R is 4 here, 4 plus 1 is 5, 5 mod 5 is 0, right? So R will become 0. R will become 0. Right? R will become 0. Let's not make the change here. I'm just checking whether the queue is full or not. So I'm not making change to R. Right? So R was 4. So I said after incrementing R becomes 0. Right? Now this incremented R, right? circular incremented R is incremented R. Incremented means circular incremented R equal to F, right? Right. That is, after, like in this previous case, right? In this previous case, here you see incremented R was 0 and F was also 0. That means the element was present here. In this case, we concluded that the queue is full, right? Incremented R is equal to F, right? So that is queue full condition here. But here, incremented R is 0 and F is 2. Incremented R is 0 and F is 2. They are not same. That means there is space here, there is space here, right? Incremented R is 0 and F is 2. So they are not same. That means there is space here and I can insert new element here on incremented R position, right? That is 0th position. So I can insert 60 here. I can insert 60 here. So that is how insertion happens in the circular queue, right? So deletion also happen by using the same circular formula, circular increment. Insertions also happen by using the same circular formula. So this is queue full condition here. What is queue full condition? I'll write queue full condition. Full. So increment R by using formula. What is the formula? R equal to R plus 1 mod size, right? First step. Second step is if R, now what is the R? Incremented R I'm talking about. Incremented R. If this incremented R equal to F, right? If incremented R equal to F, right? So plus plus R I'll write here, not plus plus R, but R incremented using this formula. Or rather, I'll say directly right here, if R plus 1 mod size, this will give me incremented R equal to F. If this is same, right? Whatever, I'll get some value by this formula, that is the incremented R. If that incremented R is equal to F, right? If that is equal to, if they are same, then we'll say that queue full. Queue is actually full. There is no space. There is no space, neither from the front, from any end, right? There is no space from any end, right? So this is the queue full condition here. Okay. So I hope you understood. So we'll see an example of NQ and DQ operations on a circular queue in the next video. So I hope you understood this. So see you there. Thank you.